All right, so we're going to talk about Chapter 8, Rotational Motion. This is part of my 5th unit, where I combine it with circular motion. The concepts are very similar, but there's definitely some distinctions that we need to make. So, here is some of the info that I want to express right off the bat. I want to make some comparisons here between linear and angular motion. So in this case, we have angular displacement. So where we had linear displacement was represented with the letter x. But now it's going to be represented with the Greek letter theta. And so just like how before we had delta x is equal to x minus x naught, or you could express it as x2 minus x1, which is more of the comparable sort of way that it's being expressed here. Okay, it's the same thing, it's your second position minus the first. It's just that this is a angular position, right? It's how many radians are you away from your initial position, right? So radians for us often is not as intuitive as thinking of it like degrees of angle, but they are in fact the same thing. And so radians is the angular unit of measurement. Now keep in mind that a radian is more of an idea rather than an actual measurement, because how do you have you have a circle, right? And 2 pi radians is one complete circle. That is a terrible circle, I'm sorry. But keep in mind that 2 pi radians is one circle. So how do you come up with pi? Well, like, what is pi measured in? And so pi is the circumference divided by the diameter. And keep in mind that that is meters divided by meters. Meters cancels out, and you're left with radians. So radians isn't so much of a unit per se as an idea. Just like how one revolution isn't really a unit, it's more of an idea. So keep that in mind, because radians has the tendency to just kind of like appear and disappear. Also keep in mind that we don't need to worry about having our calculator in radian mode, because unless we're taking like the sine, cosine, or tangent of an angle, we don't need to worry about it being in radians. And we are not going to be doing that in this class, where you can keep your calculator in degree mode. Okay, so what about angular velocity? So linear velocity is v, obviously, and that is going to be equal to your change in linear position per time. Well, angular velocity is represented with this lowercase omega. It looks like a very cursive-y sort of W. It's a lowercase omega. If you remember, an uppercase omega looks like that, and that has a different representation in physics. So we're not going to be using that. So the lowercase omega looks like a W, and so it's clearly going to be the change in angular position divided by time, and it is measured in radians per second. Okay, it is radians per second. And then with acceleration, again, since in a linear world we have acceleration is the change in velocity per time, well, for an angular acceleration, this is alpha, right? It kind of looks like a fish. When I write it by hand, it always looks like that. And so alpha, which is the angular acceleration, is the change in angular velocity per time. This is measured in radians per second squared. And my head is ever so slightly in the way, but I can change that. There we go. Okay, so since I really don't like to memorize equations, I like to look at patterns. So here's a pattern that I really want you to recognize. Here we have displacement, velocity, and acceleration. Keep in mind that this acceleration is along the tangent, this velocity is along the tangent, and I'll get into that in a moment. Also, this x displacement is along the tangent as well. In fact, I should write that in. So let me just get that written. Tangent. Okay. So the linear displacement, okay, so here's the bottom line. The linear quantity equals the radius times the angular quantity. So here we have the linear quantity, which is the x displacement, the linear displacement along the tangent. That's going to equal the radius times the angular displacement. This is measured in radians. This is measured in meters. The linear velocity along the tangent is equal to r, the radius, times the angular velocity, again, measured in radians per second. The linear quantity, the acceleration along the tangent, is equal to the radius of the circle times the angular acceleration, measured in radians per second squared. So if I were to draw a circle, let me see if I can move this stuff upwards a little bit. Give myself some space if I can manage it. There we go. And so if I were to make a circle, that's not a circle. I don't know my shapes very well. So if I were to make a circle and represent the motion that happens across a circle, so let's say that this represents some sort of arm extending out from the center of the circle, and then over the course of time, this arm moves in that direction, and then it has a second position that I'll just kind of draw. In fact, I'll make it a little bit dotted. So this is, it moves from here to here. And so in that time, it's going to move an arc length, okay, that I will express as x. This is sometimes expressed as an L, a lowercase l, like this sort of italicized cursive L, meaning arc length, but they're the same thing. Okay, this is essentially the distance that it moves along the circle. Why is it expressed in an x then? Like it's linear. Well, what if this is a wheel, and this wheel is actually moving? That's funny. I just drew a line, but the line is the same color as the background. So what if, let me change the color to black. Okay. So what if this is a wheel that is moving along the ground? Then the length along the ground would in fact be the same as the arc length. And so you could express that as some distance x, right? So this x would be the same as this length here. So that's why it's expressed that way. So keep this idea in mind. So now what about velocity? So the velocity along the tangent is equal to r omega. So let's say that the angular velocity, so there's so many radians per second. Now this thing didn't go very far, but in a certain amount of time it made this angular displacement. Well, this velocity here represents the velocity of the wheel from its center of mass. Or this would represent the velocity of the car that the wheel's attached to. In fact, this is how the speedometer on your car works. Your car assumes that there is a certain value to the radius of the wheel. If you have a Jeep, for example, and you decide to put bigger wheels on your Jeep Wrangler, then all of a sudden your speedometer is not going to work anymore because it thinks that the wheel has a certain radius. It knows that it is rotating at a certain rate, and so it gives you a readout of your tangential velocity. But if you increase this, then that's going to change this, okay? And in fact, if you think about it, if you are driving a car that you have increased the wheel size on, okay, you get a Jeep and you put some big 37-inch wheels on it. And so you're driving and your speedometer reads 55 miles per hour. Are you moving faster or slower than 55 miles per hour? Your speedo speedometer readout says 55, but you put bigger tires on it. So are you going slower than 55, or are you going to get a speeding ticket because you're going faster than 55? And the answer to that is, well, you're moving. You've increased your value of r, and so given the same number of rotations, you would be moving faster, and so you would actually be speeding and probably not really realizing it. So just a little bit of a heads up on that issue. Let's look at the difference between frequency and period. We've discussed that a couple times, but I want to make sure we have this really down down tight. So frequency, again, represented with this sort of like italicized cursive F. F is measured in, it's basically cycles per second, and or rotations per second, revolutions per second. It's all of those things. The units are cycles per second. However, it is also expressed in terms of hertz. So 1 cycle per 1 second is the same thing as 1 hertz. Period, represented with the capital T, is equal to 1 over F, where this is measured in cycles per second, and this is expressed in terms of seconds per cycle. And often the idea of a cycle or revolution or rotation is all often just kind of like canceled out altogether, and we just express it in seconds. Keep in mind that frequency and angular velocity are practically the same thing, because in one cycle you have 2 pi radians, so you can easily convert from one to the other. All right, so now we're going to start getting into this whole thing where I'm going to give you information and then you have to be able to run with it, is the bottom line. So just like I had expressed up above here, where you have this relationship, I want you to understand, and in fact, it's probably better for me to express it with this, where we have like this equation here from the linear world that we already know. You should be able to take any equation that you know from the linear world and apply the angular equivalent. So if I say, hey, here's this equation, what is the angular equivalent of this equation? You should say, okay, well, x, let's see, the angular equivalent of x is theta. So I'm just going to replace all the x's with thetas, and I make this equation. Or I do the same thing here. Turn this equation here into its angular equivalent. Okay, well, for velocity, the angular equivalent is omega. So you put that in its place, and the angular equivalent for x is theta. So you put that in its place. Okay, you need to be able to recognize to do this for any equation. So take a look at this. Every single one of our linear equations, as I write in white on white, brilliant. As we look at all of these linear equations, look at how we just make an angular equivalent. So what this means is that in this case, we have an initial velocity of, here, we have an acceleration, and we have a final velocity. Well, in this case, we have an initial angular velocity, we have an angular acceleration, we have a final angular velocity. So you should be able to take any of these equations that you already know and be able to develop this equation. I do not expect you to memorize these. Instead, I expect you to be able to have these already memorized and be able to develop these based off of it. What I will actually do is write out, whenever I'm working out these sorts of problems, I will actually on my paper write out my initial equation, x equals x naught plus v naught t plus 1/2 at squared, right? I have that memorized. And then directly below it, I will rewrite the equation in its angular form. So theta equals theta naught plus omega naught t plus 1/2 alpha t squared. Okay, you must recognize that those are basically the same equation. It's just that one applies to angular movement rather than linear movement, but they're virtually the same equation. You should now move forward recognizing that you can basically take any equation and turn it into an angular equation. Okay, and I'm going to kind of test you guys on this in a moment. Okay, so I'm going to go ahead and move on. Okay, so now we're going to look at the idea of rotational inertia. Rotational inertia is this idea of it's the same idea as mass, but in a sort of angular sort of way. Remember that linear inertia is the tendency of an object to resist a change in motion. So rotational inertia is, go figure, the tendency of an object to resist a change in rotational motion. So in the linear world, mass is the only thing that determined how much inertia you had. However, in the angular world, there's a little bit more to it. So we represent it with the letter I, capital I, and at its maximum, in fact, I actually have something here that I need to erase. Let me get rid of that 1/2. At its maximum, inertia, okay, rotational inertia, is equal to mr squared, meaning that it's equal to the mass of the object. And so let's assume here that this ball is the mass. The string is massless, and you're just whipping this ball around on a string, and all of the mass is just all in one fairly small location going around the circle. If all of the mass is towards the outside, like it is in this scenario, the string is massless and all of the mass is concentrated in this spot, then we would say that the inertia, the rotational inertia, is equal to mr squared. So this would be true either for a ball on a string or a very, very thin hoop. Okay, so like a hula hoop or some sort of like ring, okay, where all the mass is towards the outside. That is when the rotational inertia is at its maximum. For something like a solid disk, okay, so like assume that this disk is just totally, I'm going to shade it in, so it's a solid disk, it is a continuous structure, then in that case, it would have a value of 1/2 mr squared. And so there are rotational inertias for each object about which it rotates. And so here is that chart. You do not need to memorize them. You should be able to recognize them from a chart and be able to determine what to do with them. There are two that you should memorize. The first one, okay, where it's a thin hoop or a situation where the mass is all towards the outside, it's just simply mr squared. And then the other one that I believe you should memorize, I don't think it's typically forced upon you on the AP test, but trust me, it's just good practice. You should memorize the solid cylinder. So that would be 1/2 mr squared. And you'll just notice that they're all fractional values of this mr squared. So like a tin can, for example, right? Something like this. If I rotate this object like this, it has a certain rotational inertia. Notice that if I rotate it like this, however, that rotational inertia is different, okay? So this basically determines how much resistance there is to an object rotating. Okay, so to give you a better understanding of the conceptual understanding of rotational inertia, I'm going to ask for a little bit of help from you guys. Okay, so what I'm going to ask from you, if I can, okay, here's what I'm going to ask from you. I want you to take your arms right now. I'm going to take your arms. I want you to stop doing any writing. I want you to take your arms, I want you to put them out. I know that my screen doesn't entirely show my arms, but I want you to put them out, and I don't care if you're in your school classroom right now, I don't care. You're gonna put your arms out, you're gonna lock in your arms with your torso, and you're gonna rotate at your waist. You can sit down and do it, and I want you to do it as quickly as you can. And I just want you to feel how hard it is for you to actually move your body like that. Then I want you to cross your arms, and now do it. And you should feel how much easier it is for you to move your body back and forth when your arms are crossed versus when your arms are out, okay? So doing this is much easier. Doing this is much harder. By the way, if you were to take like a couple of like 5-pound dumbbells and you do it, it would be very hard to do this. It's very slow. So the more mass there is towards the outside, the more rotational inertia you have, okay? So this value of I would be much larger if you have more mass towards the outside, okay? So let's kind of go back and look at that. So the more mass you put towards the outside, the greater the value of I is. It's a very important concept. Don't forget it. We'll come back to that. Okay, so let me kind of come to this idea a little bit. So here I have this scenario where we have an inclined plane and I have these various objects. My question to you is, which one of these objects, given that they are all like, set side by side on this inclined plane, which object will make it down to the bottom first and which one will make it down to the bottom last? Now the stipulation here is that the objects all have a minimum amount of friction. So for all of these round objects, they have the least amount of friction required to get them to rotate. For the box, there's no friction because it's not going to rotate, right? So there's going to be zero friction for the box and a minimum, absolute minimum amount of friction for all of the rolling objects in order for it to rotate. So the question is, which one will make it down first, given that they're all released at the same time, versus which one will be first and last. So this is a solid cylinder. This is a solid cylinder that is just bigger. This is a thin hoop. This is a solid sphere, and this is a box. So which one will be first and last? All right, so the box will make it down to the bottom because there's no friction for it at all, and there is at least a little bit of friction for all of the wheels to rotate. The other issue is that for the box there is translational energy, and all of its energy is going to be translational when it gets to the bottom, versus for all of the rotating objects, when they get to the bottom, there will be this linear energy, but there will also be a rotational energy. Well, where did that rotational energy come from? It's got to come from somewhere. So that is another thought on that as well. So if you can imagine this being like, what if this solid one is like a bowling ball, a really heavy bowling ball? Can you imagine it like rolling down to the bottom and then it hits like a wall? What's going to happen to that bowling ball when it hits the wall? Especially if it's like a smooth, slick floor. Isn't it going to hit the wall, come to a stop, but still spin for a second before it stops rotating? Right? If you've ever gone bowling, you might have noticed that when it comes up to the top, like when you go to grab the ball, you notice it kind of spins for half a second when it comes to a stop, or like billiard balls do the same thing. Okay, so the box makes it down first, okay? Now which one's last? Well, it turns out that the thin hoop will be last, because the thin hoop, just like what we had shown, where we put our arms out and we have a large rotational inertia, when all of the mass is towards the outside, it's a larger rotational inertia, which means it has more resistance to rotating. So this thin hoop will resist accelerating more than the rest, which means that it will be the slowest one down the inclined plane. And then these two here, even though, whoops, let me switch them around. Even though this one here is larger in diameter, they actually will go down at the same rate. What matters is that ratio between its diameter and its moment of inertia. So basically, what it comes down to is that its radius kind of cancels out, and so does its mass. Okay. So that, and then the solid sphere will make it down before both of those. Let me explain why in a different sort of way. So let's look at, let's compare this and the solid sphere. So if you were to look at it like they're both coming at you, what would they look like in your point of view? So if this object here was coming at you, it would just look like a rectangle, wouldn't it? And then the sphere, when it comes at you, it would look round, right, in your perspective. And so which one has a larger proportion of its mass farther from the center? And that would be the solid cylinder. In fact, let me kind of cut out, let me let me show you. If I were to, I'd have to like take out a little bit of the mass. So if I'm going to shade in the area, I'm going to shade in the area that the sphere does not have, right? In fact, let me overlay them. Let me overlay them. I guess it's not a very good overlay. Let me make this sphere smaller. There we go, that's better. Something like that. So you can see that there's a little bit of area here. Okay, there's a little bit of area here where if I shade this in, that's mass that the cylinder has farther from the center that the sphere does not have. So therefore the solid cylinder has a larger rotational inertia than the solid sphere has. So the sphere would make it down faster. All right, let's move on. Let's look at rotational kinetic energy. So rotational kinetic energy is 1/2. What is this? Think about this. Isn't this effectively mv, right? 1/2 mv squared? But it's not mv. This is the rotational equivalent of mass, which is rotational inertia, and this is the rotational equivalent of velocity, which is angular velocity. By the way, rotational velocity and angular velocity are the same thing. Okay, you can say either one. It's usually angular velocity is the term used, but one is not more right than the other. So your total translational kinetic energy would be its linear energy of 1/2 mv squared plus its rotational kinetic energy. This cm just simply refers to measuring at its center of mass. And the reason why this is a capital M is just to denote that the object is in fact rotating. That is not capitalized for any other reason. Okay, this can be helpful just to help express that it is in fact a rotating object. So an object's total kinetic energy is going to be both, right? If I have a box that is a mass of 1 kilogram sliding to the right, okay, with a velocity of 1 meter per second, and it has 1 kilogram mass, and then I have a ball that is also going to the right, 1 kilogram mass, right? It's going at 1 meter per second. They both have this linear velocity of 1 meter per second. They both have the same mass, therefore they have both the same linear kinetic energy. However, the ball also has a kinetic, rotational kinetic energy. So it actually has a little bit more energy than does the box. Let's take a look at torque. So torque is a rotational force, where linear force is expressed as F equals ma. What is the angular equivalent to that? Well, we, instead of using an F, we use this Greek letter tau, okay? And instead of ma, it is, okay, so mass. What is the angular equivalent for mass? That's rotational inertia, capital I. What is the angular equivalent of acceleration? Alpha. It's the angular acceleration. So this is essentially Newton's second law, but applied to angular quantities. Okay, this is basically F equals ma. It's a rotational force, rotational inertia, rotational acceleration. Okay? All right, so let's apply that to this wrench. Okay, if you can dodge a wrench, you can dodge a ball and that whole thing, right? So we are going to take your hand, and let me change it to this sort of position. So this arrow is going to represent the force that you apply with your hand onto this wrench, and you're applying the force right at that location there. So torque not only is equal to I alpha, but torque is also equal to the force times the distance from the center of rotation. So we are using the letter R instead of X or D because we are expressing that there's rotation happening and that it is a specific distance away from the center of rotation. So that value of R. So if this is the center of rotation, this is where you're applying the force, then this is my value of R. It's the lever arm length is what it's often called. The force is applied perpendicular to the lever arm. That is why we have this little upside down T here. It's not really a T, it's actually just a symbol to represent that the force is perpendicular to the lever arm length. Now what's often done actually in textbooks, but I don't like it, is that the little perpendicular symbol is expressed with the R rather than the F. Personally, I prefer to do it with the F. So let me express kind of what I mean here and what the significance is. So what we do is this. What if you decide to apply this force at an angle? Okay, so you're going to apply your force at some angle here. So let me kind of change my arrow to represent that angle. So you're going to apply the force at an angle right there. So what we would have to do is we have to break down the force into its x and y components. Okay, so there's a component of force that goes down. There's a component of the force that goes to the left. Now I hope you recognize that the part of the force that goes towards the left, right, that goes that way, is not going to go towards any rotation whatsoever. Right? It's not going to cause any rotation at all. The only part of your force that's actually going to go towards any rotation is this part here. So you'd have to break down the force and figure out what is the force that is perpendicular to the lever arm, and then multiply that together to get the torque. Now the way textbooks often will teach it is this. It's not my preferred way to do it, but I'll explain the process. Let me kind of backtrack a bit. Okay. So the way that textbooks often express it is they will say that rather than breaking down the force into its components, instead, if there is, in fact, let me actually move it back to the way it was, rotate this guy. Okay, so if the force is being done at an angle, what you do is you take the entire force, but you multiply it by, and let me make some arrows of a different color. I'll make it green. Okay, so what you would do is you would break this down into its relative x and y components. And you're like, that makes no sense. But what you want to do is you want to find out what is this length here? How much is this, right? So you take this value of the length and multiply it by the whole force. Both work, both give you the same answer, but from an intuitive standpoint, this does not make as much sense to me, right? This is not nearly as intuitive as for me to say, you know what, I'm just going to take the whole force, or excuse me, I'm going to take the whole lever arm length, and I'm just going to break down the force into its components, and I'm going to take the part of the force that is perpendicular to the lever arm, and I'm going to multiply those together. Okay, that's my preferred way because I think it's more intuitive to understand. So that is torque. Keep in mind that the units for torque are Newton meters, right? It's newtons times meters. Do you remember how work is force times distance? This is also newtons times meters, but we instead will express it as joules instead of, right? This is the same thing as joules. This is partly to keep confusion between these two things because this is not work. They are not the same idea, because for work to be done, the force has to be parallel to the displacement. In this case, the force has to be perpendicular to the displacement. So it is very different. It's the same mathematically, but very different conceptually. So do not mix those two up. Okay, work. What is the equation for rotational work? Here we have an angular displacement of theta, we have an arc length of L, and we have a tangential force, right? A force that is perpendicular to the lever arm length of F. What is the equation for work? What is work done to cause the rotation of an object? Think about this. I'll give you guys a moment. Okay, so where linear, what did I write? Linear? I don't know what I wrote. So linear work is equal to force times distance. So since the angular equivalent to force is torque, it's a rotational force, and the angular equivalent to distance is theta. So therefore, work is equal to torque, right, rotational force, times rotational or angular displacement. Remember that torque is equal to Fr, right? So torque is equal to Fr. So this could be rewritten to where work is equal to Fr theta. Oh, hold on. X equals R theta. So if you wanted to, you could also do some substitution here where X over R is equal to theta, and you could even substitute that in as well if you wanted to or had to, right? So, and then the R's would cancel. But that's not frequently done, but it's the sort of thing you should be able to kind of recognize and do if needed. All right, let's do another one of these where you need to figure out what the equation is. Here is angular momentum. So angular momentum. What is the linear equation for momentum? What is the linear equation? All right, so for linear motion, the equation is P equals mv. For angular momentum, we have a capital L, which represents angular momentum, and that is going to equal I omega, where instead of mass we have rotational inertia, and instead of linear velocity we have angular velocity. Okay, L is I omega. Okay, so let's see if we can look at this conceptually. Now, the same concepts apply from linear motion to rotational motion. Listen, I want you guys to hear me on this. Listen. Any concept that you have learned up to this point can be applied to rotational or angular motion. Think of Newton's laws. An object in motion stays in motion, and an object at rest stays at rest unless acted upon by an unbalanced net force. Okay. An object in rotational motion stays in rotational motion. An object in rotational rest stays in rotational rest unless acted upon by an unbalanced, non-zero net rotational force, or torque. Newton's second law, we already applied. Newton's third law. For every action rotational force, there's an equal and opposite reaction rotational force. Okay, so keep this in mind for rotational or angular momentum. It's conserved as long as there's not outside forces. So what if you and I were in dead space, right? And I cause you to rotate. I'm like, ooh, I don't like you. I'm going to make you spin. Guess what's going to happen to me? I'm going to spin the other way. That's the way it works. Okay? So that's why when you see, you guys ever watch like guys do dirt bike jumps on TV? Right? Those guys go off of a jump and they do these crazy tail whips where the bike comes up and it seems like it just defies the laws of physics. It's because they are causing the bike to rotate one way, right? The wheels are causing torque one way, and there's something else rotating the other. Think of, and I used to ride dirt bikes and I used to do jumps. Nothing crazy, but enough to where like I was like, uh-oh, I'm getting myself in trouble. I better sell my bike so I don't die. And so when I would go off of a jump, this is something I really learned. If I was about to face plant because I just screwed up the jump and I'm about to face plant, you know what I would do? Hit the gas. Because the wheel rotates one way and the rest of the bike rotates the other, and it would pull up the bike. Or what if I'm aiming towards the sky? Slam on the brakes. The wheel accelerates one way and the bike has a rotational acceleration the other way. So angular momentum is conserved. And this is something that is great for flywheels. This also works in terms of if you've ever seen somebody who, and let me make myself a little bit bigger for this. So if you've ever seen like an ice skater, right? They go and then they pull in their arms and they start spinning really fast. It's because they have a large value of I. They increase their value, they have a large value of I and they decrease it, right? They have a large rotational inertia and then they decrease the rotational inertia, which is going to make their angular velocity increase. In fact, this is pretty cool. If an ice skater had weights in their hands, or what if they like wore gloves that were weighted, they would have a really large rotational inertia. And when they pull in their hands, they would spin even faster. Okay? So this is something I often will do in my classroom where I have like these rotating platforms that you can stand on. You actually take 5-pound dumbbells and you pull them in and you spin way faster than you have control. And it's super, super fun. Okay. Let's see if there's, think figure skater, right hand rule. So there's a right hand rule thing. I think that what I will wind up doing is posting. So basically what this means is that rather than saying that this thing's rotating counterclockwise viewed from above, instead you would say that this thing has a rotation that is up. You take your hand and you wrap your hand around this object, and the direction that your thumb points is the direction of its rotation. And you say it's rotating upwards. Is it actually physically moving upwards? No. It's just so that way, whether you're looking at it from below or above, everybody can agree on its direction of rotation. So if I were to tell you that an object is rotating so that way it's rotating like into the page or into the screen that you're looking at right now, think about it. Take your thumb and point your right, it's your right hand rule, not left hand rule, right hand rule. Take your thumb and point your right thumb into the screen with an open hand, and then close your fingers. Think about it. Is that clockwise or counterclockwise from your viewpoint? It's clockwise, right? Take your hand, right? From my point of view, it's clockwise. And so that would be, right, if I say that it's into the screen, from your point of view, this is counterclockwise, but from my point of view, it's clockwise. But if I say that the direction of rotation is into the screen, then when we describe it, we can both agree on its direction. So it's just by rule, it's a way of determining direction of velocity, acceleration. And by the way, all coordinate planes work off of the right hand rule. Think of the X, Y, and Z axis, right? Think about it. Take your hand in the 0 X axis, sweep your fingers into a positive angle, and your thumb points out of the page towards you. Guess what? Your thumb points towards the positive Z axis, because a coordinate plane works off of a positive right-hand rule. And then lastly, this is the conservation of angular momentum. If you are on a merry-go-round without a motor, there's no outside forces. If you are towards the inside of the merry-go-round at the middle, and you walk towards the outside of the merry-go-round, your angular velocity increases. The merry-go-round's angular velocity decreases. Okay? Action, reaction. Whew. That was a lot of content, and we are going to look back on a lot of these concepts and talk about them, because it's a lot of content. But I wanted to kind of get this all taken care of so that we can focus on it more later. All right? So that's going to do it for my recording here. So peace out on that.